Okay, so let's continue. We're at probability part, and I'm doing question number 11 from 2018, which is quite nice. Let's see. The way to explain this, I'm going to do this very systematic and focusing on 11.1. We're given 7 digits, and we're asked to make a unique code, okay, that consists of 5 digits. And then there's 2 instances. Well, when digits are repeated and when digits may not be repeated. Okay. The formulas to use for this calculation are not given at the back, so you've got to realize this. And I thought I'd just quickly give you an overview of what this really is. I don't know if you ever learned that, but it may be good just to know where to plug it into your head. And assuming, what we're assuming when they solve this problem is that order is important. Okay, so I gave you this neat little graph here, or this table. And so you have 2 options. You can either compute it as a permutation. The big assumption with permutations is that the order of these numbers, in this case, these 5 little numbers that you've randomly chosen out of the 7 numbers, that the order of that is important. And I think it's because you're creating a code or something that you're assuming that the order is important. Okay, so then you use permutation equations or formulas. But there's also another one, maybe for the future important to know. You certainly learn this in your first year at university, is combinations, and then the order is not important, right? So those are the 2 scenarios, but the assumption we've made, and that they've certainly made in the paper and the solutions, is that the order is important. And then what you can see here, well, the digits may be repeated. Well, repetition is allowed. So in the first formula, you're going to apply this top right one. And to break down that a bit, I give you a little legend here. So n in this formula is the number of objects, because it can also be objects, right? You can have a container full of balls and you can randomly pull X amount of balls. So in this case, it's numbers, but I'm writing also objects because the question might also be posed to you. Well, we've got 24 red balls and how many, and 17 blue balls. So how many, what's the probability of pulling amount of red balls when I pull 7, you know, something like that. So it can be numbers or objects. But the point is the n is the total number of objects that can be chosen from, and the r is the number of chosen objects to be chosen. So for this example, I've got 5 things that can be chosen from: 3, 4, 5, 6, 7, 8, and 9. But I'm doing a 5-digit code, so I'm only going to draw 7. Okay, so that's the breakdown of how you're going to use this table. But unfortunately, you have to know these formulas, right? They're not given for some reason. Okay, so that's 1. Let me just see how I divided these slides. It might be, okay, that I really did it very decently. Okay, so digits may be repeated, so you're assuming order is important, repetition is allowed, so you're doing that. So all it is for 11.1.1 is the total number of digits that can be generated is 7 to the power of 5. Okay. Then for the second part, well, digits may not be repeated. Okay, and what that then in essence means is you can't have this randomization, for example. There can't be 2 3s in here. That's not allowed. So that's what's meant with repetition or not repetition, just for clarity. How are you going to apply this second formula? or what that implies, and I don't know if you know what this notation means. So what that notation means, and keep in mind that n equals 7. So what this means is in essence it's 7 multiplied, we do multiplication, by 6, multiplied by 5, multiplied by 4, multiplied by 3, multiplied by 2, times 1. That's what that means, okay? And that's in the case of n equals 7. So when we apply this formula then for this example, we'll have 7 and then 7 minus 5. Okay, I'm going to write that out. So that's 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 7 minus 5 is 2, so it's going to be 2 times 1. These cancel out, and so you're going to have the solution is a huge number. It's 7 times 6, well that's 42 times 5 is 200 and something, and your solution here, I think, you can go double check me, is this. But in essence, I'm just giving you a complete sort of a backtrack of where this equation comes from. And it comes from the fact that you're assuming order is important and you're applying the formula for permutation thus. Okay, and I've also explained the difference between n and r and what this notation means over here. And that's that. So that's 11.1. And then for 11.2, okay, you're then also given n equals 7, right? But now you have to make a unique three-digit code. Okay, so r equals 3. But importantly, you're giving 3 very distinct limitations, okay, or conditions. There's no formula to this. You've really just got to think logically and apply each sort of condition by itself, okay? So let's think about this. In the case of codes, okay, and 3-digit code with repetition, for the general case then up into this first little node, okay, the formula would have been, I'm choosing from 7 numbers, only 3, okay? But now at the second condition, so condition 2, I know that the code can only be between 400 and 600. What does that mean? What does that, think about that. What does that mean? It means the first number in that code can be either a 4 or a 5. Okay, that's what it means. It has to be less than 600, so it can't be 6, and it has to be greater than 400, so it has to be 4. Okay, so the first number in that digit can either be 4 and 5. Okay, that's what this second condition means. And the third condition means, well, it has to be divided by 5, divisible by 5, okay? And because 0 isn't in the list of numbers to choose from, for this third number, the only multiple in that set of numbers of 5 is 5 itself. So the third number can only be 5. Okay? So we're choosing 3 numbers. A number 1, a number 2, and a number in the third position. For the number in the first position, well, we know now that we can only choose 2 of them. One of 2, right? So we're choosing one number but we only have 2 to choose from. So the amount of choices we have to make there is 2 to the power of 1. We're choosing one number because it's this first digit. But we can only choose from 4 or 5, so it's 2 to the power of 1. For the second digit, well, it seems that we don't have any limitations there. So we're choosing a number, but it can be chosen from 7. So for the second number, n is 7. Okay, but we're only choosing one number, so it's 7 to the power of 1. And for the third digit, we know, wow, this can only be one number. So we're choosing from one number, only one number. And that's how you compute how many different unique 3 different codes you can choose given these 3 conditions. So it'll be 2 times 7 times 1. Oh, I've already written the answer there, like a tit. 2 times 7 times 1, that is 14. So the maximum amount of unique 3 digits codes that can be generated given these 3 limitations is 14. And that is example 11, or question number 11 out of 2018.